Now, yesterday we discussed about the theoretical aspect about the current source. So we'll continue with that. And today we'll try to do some sort of simulation. Before doing some simulation, let us try to understand what is that we are going to do it in this session. So basically our objective of this session is to find that particular output resistance of a MOSFET which we will be using in the design of current source. Okay. So basically we'll try to figure out that output resistance. Now in order to find out the output resistance, so there is some procedure involved. But before that, let me just give you small inputs on how we calculate the resistance. So basically, my drain current in linear region or in triode region is given by the equation mu n C aux W by L VGS minus VT times VDS minus 1 by 2 VDS square. Now, because in the triode region, like over here, this is my ID and this is my VDS. So in this region here, in triode region, we say that we know that VDS is very small, and you can see from graph also. If you see here, the value of VDS increases. So behind this particular value here, the VDS value is very, very small. So if this VDS is very small, we can ignore half of VDS square term, isn't it? Because see, if VDS itself is small, the square of VDS will be even smaller. Like for example, if just a moment. If VDS is equal to, let's say, 0.2 volt in this triode region, then VDS square will be 0.04 and half of VDS square will be half of this VDS square will be 0.02, which is even smaller, right? So that is the reason I can ignore this particular term from this equation. So then my ID equation would result into only mu n C aux W by L VGS minus VT times VDS. And if I can bring this VDS term over here, what is that I can get? I can see that this is the same equation that we sometimes back we discussed. So we're going to see this entire mu n C aux W by L, all those things, right? So I can say, yeah. But ultimately, what is that I require? I require VDS by ID because I need to find the resistance. So that way, I can say that VDS by ID would be nothing but L by W. So basically, I can say my RDS, which is basically the resistance in the triode region. So this is how basically the resistance in the triode region is having dependency on the length. So basically the intent is R is proportional to L. That is what I want to say. Now, because here you are calculating the output resistance. Output resistance, how do we calculate? Let us try to figure out that. But basically your resistance and L are your directly proportional entities. So now in order to calculate the resistance, or in order to calculate the length of the MOSFET, and remember this is the MOSFET for which we are going to fix up the width and length, and this MOSFET we will be using henceforth in designing the current mirror. So, and that current mirror will be eventually acting as a current source, and that current source we will be keeping it forever for our upcoming projects or upcoming designs. So let us try to go ahead and try to see the simulation. So I have this particular circuit already designed. So I have kept it that way. Yeah, so basically here, what is that I'm doing over here? I have just taken an NMOS just to ensure I saved on time. I have designed it already. I just tell you. So how do I take the NMOS? I'll just press I, add instance, go to the library. Here I'll browse it. So in this library, you have to select the GPDK90 or whatever technology you are having. You can go ahead with that. If you have downloaded the same software, you will be getting with the GPDK90 nanometer technology. So here you can see GPDK90, and in that you can choose NMOS 1B and choose a symbol and just say OK. When you do that, all these parameters will come. Now here in this scenario, what I have done is, instead of keeping the parameters of length as a particular value, I have taken it as a constant variable. Basically, I have chosen L as a variable by the name L, and I have chosen the width as 10 micrometer. So this is you can choose any particular width for that matter. It doesn't have any impact. I'll try to give you some sort of assignments where you will change the width and length, and we'll try to figure out the output resistance. That is not an issue. But right now, what is that I have taken is the width of my MOSFET I have taken is 10 micrometer. So this is the total width. And L, I am taking it as a parameter so that I can vary this L during my entire simulation runtime. So I'll keep on varying this L because you know that your R is directly dependent on L. So if you keep on varying the L, you can observe the various resistances changes in the design. So I'll keep this as it is. And here at the input side, I'll just attach a simple VDC, the DC source. As you can see over here, VDC, it is from the analog lib library. And what is the DC voltage? 900 millivolts. Again, why 900 millivolts? There is no hard cut rule. I go with that particular value. You can choose any particular voltages. That all depends on what is the design specs that you'll get when you actually design the project or actually work on the project in the industry. But here I'm going with a 900 millivolts. Now, because see, you want to calculate the output resistance. So how do you calculate the output resistance? See, basically R you can calculate by using the Ohm's law, that is R equal to V by I, and for that you require certain voltage, and I anyhow there is a current over here, and where is my actual voltage, and that actual voltage whatever we are doing is here will short the DC source and will attach an AC source. Now here this itself is acting as an input now. So this voltage divided by the current whatever that is being generated by this particular voltage source which flows through this, the current which is flowing through this MOSFET, that current and this voltage source together will fetch me the resistance. And because you are connecting this source at the output side, and whatever the resistance that you obtain with this scenario, I can call that as an output resistance. And what is the structure of this particular source? This source is basically a V sinusoidal. Again, it is from analog lib library, and I have taken a DC voltage of 900 milli and AC magnitude of 1 volt. Now, what is the intent of these things? See, this DC voltage I have taken as 900 millivolt and AC magnitude. So because I need to have, I need to calculate the resistance. So I need some AC value. So for that purpose, the AC magnitude is 1 volt, and this DC voltage here, it is acting as a kind of VDD over here. So that ensures that your power supply is taken care into account. So that is your DC supply. Okay. So now let us try to check and save. And of course, grounds are done, and I have connected the body terminal to the source, and everything is done. So let us try to launch this EDL window. Launch the EDL window. Launch. Yeah. So already it is being launched. Okay, let me do one thing. I'll just quit this and I'll relaunch the ADL window one more time. Launch ADL. And because you have chosen a parameter for the length as L, so you need to get that parameter and you need to give the values of that parameter here in the ADL window. So for that, in this design variable box, I'll do right click, copy from cell view. The moment you do copy from cell view, you can see L will be fetched over here. And right now you will start your analysis with, let's say that I'm starting with 90 nanometer, or let's take some rounded off number, 100 nanometer as the length, and I'll go to analysis. Now because you have applied the AC source, you have to do the AC analysis. I'll choose the AC analysis and I'll vary the frequency from 1 to 1 gigahertz, and I'll say OK. And outputs to be plotted, select on the D schematic, and you have to choose this box which selects the drain node, and that will fetch you the drain current. And now I'll run it. Now once you run it, you'll get ID versus VDS graph in terms of frequency, and magnitude. So once it runs, there you go. You can see this is ID versus VDS in terms of frequency. Now remember, this is the exercise which we did long back to figure out R0. The same exercise we need to do. Now this is ID versus VDS. So, but right now I want VDS upon basically whatever I obtained here, ID by ID versus VDS. So, but I want the opposite of that, because here you have already seen. This is the graph which I got right now, ID versus VDS, but I want VDS versus ID. So for that, I need to take the reciprocal of this graph. So what I'll do, I'll right click on this graph and I'll say send to the calculator. It goes to the calculator, and here I'll click on the function and go to the all function and choose 1 over x. The moment you click on this, here if you see 1 by x will be attached. There you go. And now you run this with the help of this wave function. The moment you run it, the reciprocal of that is observed. So let me just change the background of the graph so that you have a clear picture. Yeah. And if you observe, the resistance, whatever that can be seen, is 480.88 1 by A. What is 1 by A? 1 is basically, see in the unit you can see 480.888, in the bracket you can see 1 by A. A is the unit of the current, that is ampere, and 1 is basically the magnitude of the voltage that you have taken, it is V. So that is the reason why I took there 1, ease of calculation. So 1 by A here nothing but V by I, that is in term means that it is it is giving you the unit of resistance. So 1 stands for the unit of the value of the voltage, and A is your ampere, the current. So 1 by ampere, which is nothing but voltage, volts upon ampere, is nothing but your resistance, and expressed in terms of ohms. So that is 480.88 ohms. So let us try to make a note of that. So let's note it down over here. So we fixed W is equal to 10 micro and L as 100 nano, and the resistance, which now you're calling it as output resistance, you got it as 480. I can take it as 480. 480 ohm. Okay, so let us try to reiterate these things, because what is the intent? Like I told yesterday, the output resistance of a current source should be very, very large. Ideally speaking, it should be infinite, and it should be very, very large. The reason I have already posted yesterday. So now the same MOSFET, whatever for which you are calculating the output resistance, this MOSFET only you are going to use in the current mirror or current source design. So by that notion, the output resistance of this MOSFET also should be very, very large. So what I'll do, I'll just I'll just keep this graph. So we'll just close these calculator things. And I'll go to this ADL window again. Now this time I'll change the L value from 100 to 500 nano. I'll keep on increasing because I want to show you that as L increases, the resistance also should increase. Now here in the plotting mode, I'll change it to new window so that the previous graph will be retained and the new graph will be attached side to the existing graph. So there you go. Again, I'll change this background. I'll go to the properties of this graph and change its background to white. And again, I'll replicate this, send to calculator. It is always better to close the calculator which you opened in the previous scenario. Otherwise, it will keep on overlapping the functionalities. Once the job of the calculator is done, it is better to close it. So right now, let's close the calculator. Yeah. So now, let's see. There you go. It is 11.35 K and in the bracket 1 over A. Again, volts per ampere. In behind that, there is a K, that is kilo ohms. So 11.35 kilo ohm. So when I changed, I have still kept the, because I'm not changing the width, right? So width is anyhow, it is constant. So let me just mark it. So this is 10 micro only. This is 500 nano. And this came out to be 11.35 kilo ohms. Now, you may ask the question, when to stop? Because there is no end to a value called as high value. Again, that's what. In the design specifications, whenever you go on to a real-time project, there will be always a mention. What would be the range of output resistance? And if you are able to meet that output resistance range for a particular value of L, you can fix up those W and L. So now this is pretty high. So let us go ahead with one more iteration and see what is that I can get. So I'll choose L also as 10 micro. W is also 10 micro. Let's try to do that. And for that, I'll go back to this EDL window and I'll change my L from 500 nano to 10 micro and I'll run again. And the plotting mode is new window. That means the previous graph won't be erased. There you go. Here again, let's send it to the calculator. Once you send it to the calculator, repeat the same step. Go to the function, go to the all function, 1 over x, plot the waveforms. There you go. But this time, what is happening? If you observe over here, it is going to have a dip. That means if I, let's say, if I increase the length, because see what is that happened over here. You first let's try to make a note of this. Now this is 1.14 mega ohm. This is pretty good. 1.14 mega ohm. So I think this is pretty good. 1.14 mega ohm. So I think we can fix up the length and width of this MOSFET as 10 micrometer by 10 micrometer, and the same MOSFET with the same length and width can be used for designing the current source. Okay, now the reason behind this thing is, see, I cannot keep on increasing the L. The moment L increases, output resistance, see, the intention of this exercise is to ensure that for all the frequencies from 1 to 1 gigahertz, the resistance should remain same. But what has happened? The resistance started to dip over here. So this should not be scenario. Now this intention over here, if you see, at exactly 10 raised to 6, that is at 1 mega ohms. If you observe the frequency here, if you observe the, let me just close this one. The frequency 1 mega ohm, 1 megahertz. The resistance is 1.12, and it starts to decrease as I go, right? So that should not be the case. So basically, intention here is the resistance should not decrease across the frequency, because you are running it from 1 to 1 gigahertz, and at exactly gigahertz range, the resistances keep on decreasing. So that should not happen, right? So what I can do is I'll try to redo one more iteration, and this time instead of 10 micro, previous was 100 micro, right? So previous was 500 nano. So now I'll go with 1 micro, and let's try to run it. We'll see for this also, and till here we'll mark it over here. So what we can do is, so 10 micro, I'll keep it here, and I'll also go for 1 micro because 10 micro is immediately it is a greater number. So 10 micro is a width is fixed, and now here I am fixing it as 1 micro. Let us try to see that, and let's not fix the length right now. Let's see what will be the value of this thing. Okay, I'll send it to the calculator, and I'll take the reciprocal of that, flip it. Yeah, perfect. Now here it is coming till a maximum frequency. There you go. So I think I can go ahead with this micro. So this is pretty good. Even it is coming out to be yeah. So it starts to decrease over here. You can see, right? So the constant frequency I can choose over here at a particular value, right? 21. So basically the resistance across all the frequency, the resistance is 36.83 kilo ohm, right? So the frequency is changing, but the resistance is constant across all the frequencies, 36.8. So I can consider it to be 37 kilo ohm. So basically what I can do is 37. That's what I told. It is not that you go ahead and choose any random value. Yeah. So I can fix up this one. Fix this W by L as final, as a final. Here what is happening is, if you fix up this 10 micro by 10 micro, basically here frequency is, or I can say here R varies across, just a moment, here R varies across frequency. So that means henceforth, in order to design our current source, I'll be fixing up my W as 10 micro and L as 10 micro, which is going to give a good amount of output resistance. Now, this is not the final. You can also go ahead and fix W as 1 micro, and you can keep on varying L. And you can see for a particular value of W by L, wherein my graph would look something like this. It should be giving you a constant resistance across the frequency. You can fix up that, and that I can make a note over here. I'll just give you the hint over here. So as an assignment, okay, I'll do one thing. I'll give that assignment as a part of a separate note, not here. I'll mention. So I'll ask you to keep W is equal to, instead of 10 micro, you keep W equal to 1 micro and W equal to 2 micro, and keep on varying L, and figure out what is the R out. and then we can decide for which all combinations we will be able to see the proper or high value of output resistance, and we can fix up that particular thing. Now, as of now, with respect to this particular design, 10 micrometer by 1 micrometer, that is W by L, which is giving you the ratio of 10 by 1 is equal to 10. So I can use this particular W by L ratio in designing the common source amplifier, current